Fine. Let's start. Number 10. The Chelyabinsk Meteor. It was a normal Friday morning in Russia, the 15th of February, 2013. People were driving to work in the dark cold, dashcams running the way every Russian dashcam runs, and then the sky turned white. Not lightning white, brighter than that. For a few seconds, the thing streaking overhead was about 30 times brighter than the sun, and people on the ground later said they felt the heat of it on their faces through the windshield glass. What they were looking at was a rock about 20 meters across, roughly the size of a 6-story building, moving faster than any bullet ever made, slamming into the top of our atmosphere. And here's the part that matters. Nobody saw it coming. Not NASA, not the Russians, not a single telescope on Earth. It came in from the direction of the sun, hidden in the glare, and the first warning anyone got was the light. Then it exploded. High up, tens of kilometers over the city, the rock couldn't hold together anymore, and it detonated in an airburst that released somewhere between 440 and 500 kilotons of energy. To put that in human terms, that's dozens of Hiroshima bombs going off at once in the sky. But it was high enough that the city underneath didn't vaporize. What reached them instead was the shockwave, and this is the detail that stays with me. The light arrived first, because light is instant. The sound and the pressure wave took a couple of minutes to catch up. So all across Chelyabinsk, people saw the flash, and they did the most human thing possible. They walked to the window to look. Thousands of them. Standing at the glass, staring up at the strange smoke trail in the sky, right at the moment the shockwave arrived and turned every one of those windows into a spray of flying glass. That's how you injure about 1,500 people without a single direct hit. More than 7,000 buildings were damaged, windows blown out across 6 different cities, and almost every injury came from the same mistake. The sky said, "Look at me," and everyone did, and the blast was 2 minutes behind the invitation. Now officially, this was a wake-up call. That's the phrase everyone used. A wake-up call for Earth. And it was. It's the largest object we've seen enter the atmosphere in over a century. And it happened not over an empty ocean or a frozen wasteland, but over a city of more than 1 million people, filmed from 100 angles. The uncomfortable truth underneath the wake-up call is simpler. We didn't detect it. A 20-meter rock carrying the punch of dozens of nuclear weapons walked right up to a major city and knocked on the window, and our entire global early warning system found out at the same moment the pedestrians did. And the only reason we're calling it a lucky day instead of a massacre is a few kilometers of altitude. It hit. We just got to keep the crater in the sky. Number 9. The falling space station. Let's talk about something a little bigger than a rock. Let's talk about a 77-ton space station falling out of the sky, and nobody able to tell you where it was going to land. The station was Skylab, America's first. It went up in 1973, and by the late 70s, its orbit was decaying faster than anyone had planned for, because the sun was more active than expected, and a puffed-up atmosphere was dragging it down. NASA wanted to save it. The plan was to send up the brand new space shuttle to nudge it into a higher orbit. But the shuttle wasn't ready in time. And so, in the summer of 1979, 77 tons of spacecraft started coming home, whether anyone liked it or not. Here's the problem with a big, uncontrolled re-entry. You can predict roughly when. You cannot precisely predict where. NASA expected it to come down somewhere between the 10th and the 14th of July, most likely the 12th. It actually began early, on the 11th, Eastern Australian time, and the debris field stretched from the southeastern Indian Ocean across a big, lonely stretch of Western Australia. Imagine that for a second. A machine the size of a house, breaking apart into glowing chunks, raining down over an area, and the best answer the most advanced space agency on Earth could give was, roughly this part of the planet, roughly this week. Whole countries spent that summer nervously looking up. There were Skylab parties. There were newspapers selling re-entry insurance as a joke. People genuinely did not know if a piece of it was going to land on their roof. In the end, most of it fell over the ocean and the empty outback, and the human cost was essentially zero. But pieces did come down near the little town of Esperance in Western Australia. And this is where the story becomes wonderful. The Shire of Esperance, this tiny rural council, looked at the smoldering chunks of American Space Station scattered across their district, and they did the only sensible thing. They wrote NASA a ticket, $400, for littering. Under the local ordinance, if you scatter rubbish across the district, you get fined. NASA had scattered quite a lot of rubbish. So, $400, please. And the best part, the part that makes this perfect, is that the United States government did not pay it. For 30 years, that ticket sat unpaid, a small rural council versus a superpower, until in 2009, a radio show in America finally raised the money and settled the debt on NASA's behalf. It's a funny story. We tell it as a funny story. But sit with the actual event for a moment. We put something enormous into orbit, and when it came back, we couldn't steer it, couldn't stop it, and couldn't tell anyone where it would fall. It landed on a country. It just happened to be the emptiest part of a country. Everything we launch has to come down eventually. Skylab is the reminder that the sky doesn't always let us choose the landing spot. Number 8. The Genesis crash. This one hurts because it was so close to being beautiful. In 2001, NASA launched a probe called Genesis, and its job was almost poetic. It flew out past the moon, opened up delicate collector plates made of ultra-pure materials, and just sat there in the solar wind for over 2 years, catching individual atoms streaming off the sun. Pieces of our own star, gathered one atom at a time. The plan was to bring them home, study them, and learn what the raw material of the entire solar system was made of. To get those fragile samples back to the ground safely, the return capsule had a careful plan. Come screaming into the atmosphere, pop a small drogue parachute to stabilize, then unfurl a big parafoil and glide down so gently that a helicopter could snag it out of the air before it ever touched the dirt. That's how precious the cargo was. They didn't even want it to land. They wanted to catch it mid-air. On the 8th of September, 2004, the capsule came in over Utah exactly on schedule. And then, nothing. No drogue, no parafoil, no gentle glide. The capsule just fell. It came down and hit the desert at 193 miles per hour, cracked open, and half buried itself in the ground. The collector plates shattered and packed with Utah dirt. So what went wrong? This is the part that's almost unbearable. The capsule had a set of little sensors called gravity switches, whose entire job was to feel the deceleration of re-entry and say, okay, we're slowing down, fire the parachutes. 4 of these switches had been installed backwards, upside down, because the design drawings they were built from were wrong. The switches worked perfectly. They were just pointing the wrong way, so they could never feel the deceleration. So the signal to open the parachutes never came. A drawing error. A tiny orientation on a tiny part, mounted the way the flawed schematic said to mount it, and a mission that flew flawlessly for 3 years and traveled millions of kilometers ended face down in the desert at nearly 200 miles an hour. But here's the twist, and it's the reason I actually love this story. It wasn't a total loss. The scientists went out into that desert, and they carefully, painstakingly picked through the wreckage, and they discovered that some of the captured solar wind atoms had survived the crash. Embedded deep enough in fragments of the collectors that the impact hadn't destroyed them. They cleaned them. They analyzed them. And 20 years later, that broken mission was still producing real discoveries about what the sun and the early solar system are made of. So it's a disaster, yes, a self-inflicted one. Not a rock from space, not a solar storm, just human beings and a wrong drawing. But it's the rare disaster that still handed us something true. We reached out and grabbed a piece of the sun, dropped it in the dirt at 200 miles an hour, and it still whispered its secrets. Number 7. The rehearsal on Jupiter. For most of human history, the idea of a comet or an asteroid smashing into a planet was theoretical. Something that maybe happened long ago, maybe killed the dinosaurs, maybe explained a crater somewhere. Nobody had ever actually watched it happen. Then, for 1 week in 1994, we did. And it rewrote how seriously we take this. The story starts with a comet named Shoemaker-Levy 9, discovered in 1993 by Eugene and Carolyn Shoemaker and David Levy. When they found it, it was already strange, because it wasn't a single comet anymore. Jupiter had gotten hold of it. On a previous close pass, the planet's immense gravity had physically torn the comet apart, ripping the nucleus into about 21 separate fragments, strung out in a line like a string of glowing pearls. Astronomers looked at the math and realized something astonishing. On the next orbit, that whole string was going to hit Jupiter. For the first time ever, we could predict a cosmic collision before it happened. We knew the date. We knew roughly the time. We pointed every telescope we had, plus the Hubble in orbit, at Jupiter, and we waited for the impacts to begin. Starting on the 16th of July, 1994, the fragments came in, one after another, over the course of about 6 days. They slammed into Jupiter's atmosphere at around 137,000 miles per hour. The 3 biggest chunks were each more than a kilometer across, and the original comet before it broke apart was probably around 1.4 kilometers wide. Not enormous by cosmic standards, just over a kilometer, and the energy was almost impossible to hold in your head. The combined force of all those impacts was estimated at something like 300 gigatons of TNT, thousands of times more energetic than the entire nuclear arsenal of the whole planet Earth, detonated in less than a week on a world next door. The impacts left marks. Dark bruises in Jupiter's cloud tops, some of them as large as the entire Earth. Single scars, from single fragments, bigger than our whole planet. And they didn't fade in minutes. Some of those bruises stayed visible for months, easily seen through backyard telescopes, so that ordinary people could look up and watch the aftermath of the largest impact humans have ever witnessed. Now, here's the thing everyone said afterward, and it's true. Jupiter is, in a sense, our bodyguard. Its gravity is so strong that it sweeps up a lot of the comets and debris that might otherwise wander into the inner solar system toward us. That week in 1994, Jupiter took a hit that we didn't have to. But there's a colder way to read the same event. A kilometer-wide object hit a planet, released the energy of thousands of nuclear wars, and left scars the size of Earth. And we watched it, live, from the front row. Everything we tell ourselves about impacts being rare, being ancient, being unlikely, ran into a very simple fact. It just happened. On schedule. To the biggest planet in our sky. It was a rehearsal. Jupiter played the part of Earth, and the performance was flawless. Number 6. The Tunguska event. Now, let's bring it back to Earth, and back in time, to the morning that a piece of the sky exploded over Siberia and flattened a forest the size of a city, and yet left no crater at all. It was the 30th of June, 1908. A little after 7 in the morning, local time, over the valley of the Podkamanaya Tunguska River, one of the emptiest places on the planet. Witnesses many kilometers away described the same thing. A column of blue light, almost as bright as the sun, moving across the sky. Then a flash. Then a sound like artillery, and a shockwave strong enough to knock people off their feet and shatter windows hundreds of kilometers away. Something had entered the atmosphere. Most likely a small asteroid, maybe a few tens of meters across, moving at cosmic speed. And a few kilometers above the ground, somewhere between 5 and 10 kilometers up, it couldn't survive the pressure anymore, and it detonated, not on impact, in the air. The energy released was staggering. Estimates run up to around 15 megatons of TNT. Call it 1,000 Hiroshima bombs going off at once in the sky. The blast wave rolled outward and flattened the forest below in a vast radial pattern. Roughly 2,000 square kilometers of trees, something like 80 million of them, knocked flat, all lying pointed away from the center like matchsticks swept by a giant hand. An area larger than many major cities, leveled in an instant. And here is the eerie part. When expeditions finally reached the site years later, they expected a crater. A big hole in the ground where the thing landed. There wasn't one, because the object never landed. It blew itself apart in the air and dumped nearly all of its energy into the atmosphere as a shockwave. The trees directly under the blast, at the very center, were actually left standing upright. Stripped of their branches and bark, scorched, but still rooted, because the wave came straight down on them instead of sideways. A ghost forest of bare poles, ringed by 100 kilometers of devastation. The human death toll was almost nothing. A couple of people, maybe. And the only reason for that is pure geography. Tunguska is nowhere. It's deep, remote, empty Siberian taiga. And in 1908, almost no one lived there. So let's do the math that scientists have quietly done ever since. The Earth rotates. It turns once a day, carrying every city on its surface around like passengers on a wheel. That object arrived at a specific moment, and at that moment, the empty Siberian forest happened to be turned toward it. Shift the timing by just a few hours, and it's not the forest facing the sky. It's a European capital, or a city in Russia, or anywhere else along that line of latitude, full of people, full of glass. Same rock, same blast, same 15 megatons, different real estate underneath. Tunguska wasn't ancient history, and it wasn't a dinosaur killer. It happened in the 20th century, within the lifetime of people's grandparents, and it proved that a rock too small for us to reliably find can erase a metropolis worth of ground. It just picked the one place on Earth where there was nothing to erase. Number 5. The storm that blew up the sea. Up to now, we've talked about rocks. Solid things you can point at. But some of the most dangerous things the cosmos throws at us are invisible, and they come from the one object in the sky we trust the most. The sun. In early August of 1972, a single sunspot on the sun's surface went into a rage. Between the 2nd and the 4th of August, it fired off a series of brilliant, violent flares, blasting radiation and a huge cloud of charged particles straight at Earth. And this cloud moved fast. Really fast. The shockwave crossed the entire distance from the sun to the Earth, 93 million miles, in about 14 and a half hours. That's a record. Normally that trip takes days. This one made it in less than a day. Now here's the first strange consequence, and it's one that stayed classified in the details for a long time. Off the coast of Vietnam, near the port of Haiphong, the United States Navy had seeded the water with sea mines. These were magnetic mines, designed to sense the change in the magnetic field when a big steel ship passed nearby, and detonate. Clever, sensitive triggers. On the 4th of August, 1972, dozens of those mines suddenly detonated, all at once, with no ships anywhere near them. Naval researchers were baffled, then alarmed. And when they finally traced the cause, the answer came from 93 million miles away. The solar storm had disturbed Earth's magnetic field so violently that the mine's magnetic sensors thought a ship was passing, and they blew. The sun reached down through the ocean and set off a field of naval weapons. Thousands of mines, by some accounts, cleared in a matter of days by space weather. That alone would make this a story. But it's not why this event keeps space scientists up at night. Here's why. Look at the calendar. August 1972. The crew of Apollo 16 had come back from the moon in April. The crew of Apollo 17 would launch for the moon that December. This monster storm hit right in the gap between the two missions. A few months on either side, and there would have been astronauts out there. In transit to the moon, or worse, standing on the lunar surface, outside the thin metal of the spacecraft, with no atmosphere and no magnetic field to shield them. The radiation dose from that storm for an astronaut caught in the open has been modeled at somewhere between 1,000 and 4,000 millisieverts. That is not a discomfort. That is acute radiation sickness. At the high end, that is a potentially fatal dose. An Apollo crew hit by that storm on the way to the moon would, at minimum, have had to abort and race home for emergency medical care. On the surface, in a suit, it could have killed them. And the only thing that stood between the sun and a dead Apollo crew was timing. The storm arrived in the empty space between two missions. Nobody planned that. Nobody could have. We got lucky on a calendar. We think of the sun as the source of all life, and it is. But in August of 1972, it detonated a minefield from 93 million miles away and came within a few weeks of killing astronauts, and most people have never heard a word about it. Number 4. The City Killer. Let me take you back to the 25th of July, 2019. On that day, an asteroid passed by the Earth, closer than many of our own satellites' orbit, and we found it about 24 hours before it arrived. The asteroid is called 2019. Okay, boring name, terrifying object. It was somewhere between 60 and 130 meters across. Big enough that astronomers gave it a nickname that tells you everything. They called it a city killer. Not a civilization ender. Not a dinosaur killer. Just a plain, straightforward, wipe out a city-sized asteroid. One expert estimated that if it had hit, it would have struck with more than 30 times the energy of the atomic bomb dropped on Hiroshima. And it passed within about 70,000 kilometers of Earth. In cosmic terms, that's a graze. That's the bullet parting your hair. And we did not see it coming until it was basically on top of us. It was finally picked up by a survey in Brazil, just about a day before closest approach. A day. Now think about what that means. If the trajectory had been slightly different, if that rock had been aimed at Earth instead of just past it, the entire warning humanity would have received would have been roughly 24 hours. One day to notice, confirm, calculate, and tell an entire city that the sky was about to open up. There is nothing you can do in 24 hours. You cannot deflect it. You can barely evacuate. So why did we miss something the size of a skyscraper until the last day? The answer is genuinely uncomfortable. Part of it was that the asteroid was coming from a direction near the sun, lost in the glare, the same blind spot that hid the Chelyabinsk rock. And part of it is just that these objects are dark and small, and the sky is enormous, and there are far more of these things out there than we have eyes to track. To be seen at all, 2019 OK had to be close enough to reflect a decent amount of sunlight back at us. And by the time it was that close, it was days away at most. Now, the reassuring version of this story exists, and it's fair to tell it. No impact happened. We're building better telescopes specifically to close this sunward blind spot. And just 3 years later, in 2022, NASA slammed a spacecraft into a small asteroid on purpose and successfully changed its orbit, proving that if we get enough warning, we can actually nudge one of these things off course. But notice the condition buried in that hope. If we get enough warning, deflection needs years of lead time. 2019. OK gave us 1 day. DART needed to know the target existed long in advance. A city killer that comes out of the sun, invisible until the final day, hands you exactly none of the warning that our one real defense requires. We like to imagine our planet as watched over, monitored, protected by a global net of telescopes and clever people. And it is, partly. But in 2019, a rock big enough to flatten a city walked right through that net, and we counted it after it had already passed. The truth isn't that we're defenseless. The truth is that our defense depends entirely on seeing them coming. And sometimes we simply don't. Number 3, the Kessler syndrome. Here's a disaster that hasn't happened yet, that might already be happening slowly, and that could quietly lock the entire human species onto the surface of this planet for generations. And the strange thing is, it doesn't need a single new rocket, a single new mistake, or a single new impact to unfold. Once it starts, it runs on its own. Back in 1978, a NASA scientist named Donald Kessler, working with a colleague named Burton Coeur-Palais, published a paper with a chillingly simple idea. He was studying how asteroids grind each other into dust over billions of years through collisions. And he realized the same process could happen in low Earth orbit, except thousands of times faster. In decades, not eons. Here's the logic. We keep putting things into orbit. Satellites, rocket stages, bits of hardware, and things in orbit occasionally collide, or explode, or just fall apart, and every time they do, they create a cloud of debris. Little fragments, screws, shards of metal, flecks of paint, each one traveling at many kilometers per second, fast enough that even a tiny fleck hits with the force of a bullet. Now those fragments themselves can hit other satellites, which creates more fragments, which hit more satellites. And Kessler's insight was this. There is a certain density of stuff in orbit above which the whole thing becomes self-sustaining. Above that threshold, the rate at which new debris is created by random collisions becomes greater than the rate at which the thin upper atmosphere naturally drags old debris back down to burn up. And once you cross that line, the debris population starts growing on its own, without a single new launch. A collision creates fragments. The fragments cause more collisions. Those create more fragments. And it cascades, exponentially, feeding itself. That's the Kessler syndrome, a chain reaction in orbit. And the nightmare end state is that certain altitudes, certain orbital shells around the Earth become so thick with lethal high-speed debris that you simply cannot fly through them. Not with a satellite, not with a crewed spacecraft, not with anything, because anything you send up gets shredded on the way. We would be sealing ourselves in, wrapping our own planet in a cage of shrapnel of our own making. And here's the part that should get your attention. As of the mid-2020s, there are tens of thousands of active satellites up there, and a single company is flying close to 10,000 of them on its own. Many experts argue we have already crossed the density threshold that Kessler warned about back in 1978, that the ingredients for the cascade are already assembled, and the only question is how fast the dominoes fall. Now, to be fair, the term gets overhyped. This is not a Hollywood scenario where one collision instantly fills the sky in an afternoon. The realistic version is slow. It plays out over years and decades, and we're not helpless. There are serious proposals to actively remove debris, to track objects better, to manage orbital traffic like we manage air traffic. It's a problem we can, in principle, still get ahead of. But sit with the shape of it for a second. Every other disaster on this list comes from out there. A rock, a comet, the sun. This one comes from us. It's the one cosmic disaster we are actively building, piece by piece, launch by launch, and the end game isn't fire or a shockwave. It's a locked door. A generation that looks up at the stars through a haze of our own wreckage and cannot get past it. We spent all of history dreaming of leaving this planet. It would be a very human tragedy to trap ourselves here with the litter of trying. Number 2, the Carrington event. I want you to imagine the entire modern world going dark. Not for an afternoon, not for a storm, for months, maybe years. And I want you to understand that this is not science fiction. It's happened before, in 1859, back when the most advanced electrical technology on Earth was the telegraph. The only reason it wasn't a catastrophe then is that we barely had anything electrical to break. Today, we have everything. On the 1st and 2nd of September, 1859, the Earth was hit by the most intense geomagnetic storm in recorded history. The day before the worst of it arrived, a British astronomer named Richard Carrington was sketching sunspots when he saw something no one had ever documented. A sudden, brilliant flash of white light on the surface of the sun. He was watching a solar flare erupt in real time, and it was aimed at us. The cloud of charged particles it threw off crossed the 93 million miles to Earth in about 17 hours, moving at something like 2,300 kilometers per second. When it slammed into our magnetic field, the sky lit up. Auroras, the northern and southern lights, normally something you only see near the poles, blazed across the sky all the way down into the tropics. People saw them in the Caribbean. They were so bright that in some places birds started singing and workers got up and started their day, convinced that dawn had come in the middle of the night. It was beautiful. It was also frying the only electrical network humanity had. Telegraph systems around the entire world began to fail. Operators reported sparks leaping from their equipment, shocking them, setting the paper on their desks on fire. And then the truly strange part. Some operators discovered they could disconnect their batteries entirely, unplug their power source completely, and keep sending messages anyway, running purely on the electrical current. The storm itself was inducing in the wires. The sky had become the power supply. The atmosphere was pushing so much electricity through the lines that the human-made power was redundant. In 1859, that meant some scorched telegraph offices and a light show. Now do the thought experiment that space weather scientists do constantly. Run the exact same storm today. Today, everything is the telegraph. Every power grid, every transformer, every satellite, every pipeline, every undersea cable, every data center, every hospital, every water treatment plant that runs on electricity, which is all of them. A Carrington-class storm induces enormous currents in long conductors, and the most vulnerable pieces are the giant transformers that anchor the power grid. Those currents can overheat them and destroy them. And here's the killer detail. Those big transformers are custom built. They take months or years to manufacture, and there is no warehouse full of spares. If a solar storm fries hundreds of them across a continent at once, you cannot just swap them out. Estimates for the damage of a modern Carrington-level event run as high as $2 trillion, with parts of the grid potentially down not for hours, but for many months. Think about what months without power actually means. No refrigeration, no water pumping, no fuel pumping, no payment systems, no communication. The entire fragile machine of modern civilization runs on a current that a big enough solar storm can simply switch off. And it is not a question of if, it's a question of when. Storms this size have hit the Earth before, more than once. The 1859 event was simply the biggest we happen to have instruments watching for. There's nothing special about our era that makes us immune. If anything, we are more exposed than any generation in history, because we have wired every corner of our lives to the grid. We do have some defenses now that Carrington's contemporaries didn't. We watch the sun constantly, with spacecraft like the Solar Dynamics Observatory, and with the space weather forecasters at NOAA. We might get a warning of hours before the worst of a storm arrives, enough time, in theory, for grid operators to disconnect the most vulnerable transformers and ride it out. But that plan depends on getting the warning, believing it, and acting in time, across dozens of countries and thousands of operators, all at once, for a storm most of them have never experienced. The sun did it once, when we had almost nothing to lose. The next time, we have everything plugged in. Number 1, the super flare. Everything we've talked about so far, we survived. The meteors missed the cities. The station fell on the desert. The solar storm hit between missions. So let me end with the one that we may not get a vote on. The possibility that our own sun, the calm, dependable star we've orbited for 4.5 billion years, is capable of something so violent that it would make the Carrington event look like a warm afternoon. And the evidence for it comes from watching thousands of other stars just like ours. For years, NASA's Kepler Space Telescope stared at one patch of sky, watching over 100,000 stars at once, looking for the tiny dips in brightness that reveal orbiting planets. But it saw something else too. Every so often, one of those distant stars would suddenly flare, brightening dramatically for a few hours, releasing a burst of energy thousands of times more powerful than anything our sun has ever produced in the age of human record-keeping. Astronomers called them super flares. At first, there was an easy comfort. Maybe super flares only happen on young, fast-spinning, violently magnetic stars. Nothing like our steady, middle-aged, slowly rotating sun. But then, the work got more careful. In 2019, a study led by a researcher named Yuta Notsu, published in a major astrophysics journal, went through the data and found something we didn't want to find. Many of the stars producing these superflares were, in fact, just like the sun. Same temperature, same slow, sedate rotation. Ordinary, quiet, sun-like stars, occasionally unleashing flares thousands of times beyond anything in our history. And their conclusion was cautious, but it was clear. A star like our sun should be capable of a superflare too. Rarely. Perhaps once every few thousand years. But capable. Now, a few thousand years is a long time by human standards, and that's the reassuring part. But here's the detail that turns reassurance into unease. We have only been recording the sun's behavior in detail for a few centuries. Our worst confirmed event, Carrington, is 160-odd years old. A cycle that turns once every few thousand years could easily have last turned before we had any instruments at all, before we had a grid to lose. And when scientists went looking in the natural record, in the growth rings of ancient trees, they found something that makes you sit up. There are spikes, sudden, dramatic jumps in a form of carbon called carbon-14, which gets produced when a flood of radiation hits the atmosphere. The most famous is locked into tree rings from around the year 774, a spike so large it represents something like 20 times the normal yearly variation. A wave of radiation far beyond any storm we've measured, arriving all at once. Something enormous hit the Earth in the 8th century. And to be honest, and I want to be honest here, scientists still argue about exactly what it was. Some think a giant solar event. Some think the numbers don't quite fit an ordinary superflare, and the cause is still genuinely unknown. The tree rings record the blow. They don't sign the attacker's name. But that's almost the most unsettling part. Whatever it was real. It was extreme. And it happened while human beings were alive and writing and building, and nobody at the time understood that the sky had just tried to hurt them. They had no grid to lose, so they lost nothing but a strange year. We are not so lucky. We have wired our entire existence to the very thing a superflare would come to break. And so we arrive at the real shape of it. We call the sun a life giver, and it is. Every calorie you have ever eaten, every breath, every warm day, traces back to it. But the same star that made all of that is a churning ball of magnetized plasma the size of 1,000,000 Earths. And the physics that lets it warm your face is the same physics that, on stars we can see right now, produces flares that could scour a planet's technology in an afternoon. The sun has done nothing terrible in all of recorded history. That is not a promise. That is just a small sample of a very long story. We spend so much time afraid of the dark, afraid of the asteroid in the black, the comet out past Jupiter, the cold, empty void. But the oldest, closest, most familiar object in our sky, the one thing we never think to fear, is a loaded gun that has simply never happened to point at us during the brief, bright, plugged-in flicker of time that we've been paying attention. And whether it stays pointed away is not a thing we get to decide. We just get to keep looking up and hope the trigger stays quiet a little longer. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.